All right, we're going to do some modeling with some Legos to show conservation of mass. So if you are conserving something, it means you're saving it, which means the input or the reactants has to be the same as the output or the products. And so if we look at equation 1, we have a sulfur atom as an input and an oxygen molecule as an input. And so this little 2 after that oxygen atom indicates that you have 2 oxygen atoms that are connected together. If we look at the product we want to make, we're trying to make sulfur trioxide, which is a sulfur connected to 3 oxygens. If you look so far, we do not have enough oxygens to make this sulfur trioxide, so we're going to have to add more. However, because our formula says O2, I can't just stick this lonely oxygen in here. That would have 6 valence electrons. It would not have the octet, and so it needs to come in as a bonded pair. The formula says O2, so you can only add O2. Now we would have enough to build our product. And so we could build a sulfur connected to 3 oxygens. And this is obviously not going to be true to shape that we talked about, but we have them all connected. The problem now, though, is that we only used 3 of our 4 oxygens. So that means we're going to have to build another product. And so if I do that, and I squeeze in another sulfur trioxide, the amount of stuff that I have over here on the product side has to match what we have on the reactant side. And so now I have 2 sulfurs on that right side, which means over here on the left, I also need 2 sulfurs. Notice these ones are not connected because there is no subscript there. Over here on the right, I have a total of 1, 2, 3, 4, 5, 6 oxygen atoms. So far, I only have 1, 2, 3, 4 oxygen atoms on the left side. So I'm going to have to add in a whole nother oxygen molecule. I'm just going to stack it in there. And so now we have the same number of yellow sulfurs on the reactant side as we do on the product side. We have the same number of oxygen blue atoms on the reactant side as we do on the product side. And so at this point now, our input is the same as our output. But we need to have some way to show within our equation here how many we have of everything. And so we've talked about these subscripts in the past, and these subscripts tell you how many atoms are within the molecule. When we have multiple atoms that are separate from each other or multiple molecules that are separate of each other, we're going to add something called a coefficient. And so we have 1, 2 separate sulfurs. I'm just going to scooch this stuff out of the way here. We're going to add a big 2 coefficient in front of the sulfur. And that 2 only applies to the sulfur because there's a plus sign here. So anytime there's a plus sign, that's a break. We have 1, 2, 3 oxygen molecules, and so we're going to put a coefficient of a 3 in front of the oxygen. If you look here, you have 3 times 2 would give you 6 individual atoms. So 1, 2, 3, 4, 5, 6 individual atoms. Over here for our products, we built 2 separate sulfur trioxides. So we're going to put a 2 coefficient in front. Because there's no plus sign in here, this 2 is going to apply both to the sulfur and to the oxygen. So for the rest of these, if you have Legos at home, go ahead and try to do some building on your own. Otherwise, at the minimum, do some modeling. Grab a couple of colors. So we have an individual sulfur. We have oxygen molecule, oxygen molecule, oxygen molecule. Then over on this side, you're going to have a sulfur, attached to 3 oxygens. And then you need to draw a second one because you have a 2 coefficient. So sulfur attached to 3 oxygens. And so we're going to post a few more pictures of us having modeled these, and you're going to be responsible for looking through your packet and trying to identify which of these equations is shown by the modeled things that we've shown.